Okie dokie. So let's talk about these two little background questions here on this lab handout. What is heat? Can anyone tell me what that is? Heat. What is heat exactly? We've been throwing that term around a lot. And remember what it is up top of their heads? Officially, heat is a transfer of energy. Okay, so when energy is transferred, we're talking about heat. And so we always talk about the direction of heat. Okay, oh, it's always going from what to what? Let's see here. Stick me! Always going from high temperatures to low temperatures. So you guys may recall last week we were like putting the red H in a box and the blue L in a box, and we're always giving the arrows like this, boom, just like that. So energy will always go from a high temp to a low temp. That's what's always going to happen. Okay, so we are going to talk about this little lab that you guys would normally do yourselves. So I'm going to call out some numbers. We're going to scroll down to this data table here. We're going to get our initial data. All right. So here's the setup that we have over here on my right for you virtual folks. So we have metals tied on the strings like this. You guys can kind of see that. They are plopped into a beaker of water, and this beaker is boiling. It's been boiling for several minutes now. So I'm going to go ahead and I'm going to turn my camera so you guys can see what's going on over there. And I'm going to have my 3 volunteers meet me back over there. So let's see here. Something like that. How's that camera angle looking? All right. Hey, mic check. Grace Bryles, can you hear me still?
Yeah.
Great. Okay. I'll talk really loudly. So here's what I want you 3 to do. You're going to take, just be careful because it's kind of hot. Grab it by the string. Okay. You're going to plop it into your water and get the final temp. But before you do that, I'm going to have you guys call out the initial temps of your water right here. So I'll call on you guys 1, 2, 3. You get your initial temps. Once you give me your initial temp of your water, take this little guy out, plop it in there, and sort of stir it around so the temperature can mix. Okay? All righty. So first up, we're going to get the temperature of the lead. So initial water cup. Let's see here, Austin. What's the initial temperature of your water cup?
25.7 degrees Celsius.
25.7. Okay. Oh wow. Here we go. Go ahead and plop that metal in there then, Austin. Mr. Pate, what's your temperature?
24.0.
24.0. Go ahead and plop your metal in there. Lacquer?
23.0 degrees Celsius.
Okay. Go ahead and plop yours in there as well. Okay. Now stir them around for a minute. So they're taking their little metal that's been boiling. Okay. They've been boiling that metal, and they're going to plop it in the water, see how the temperature changes. Mr. Schwender, what happened to the temperature of your water? What's it at now?
It increased to 27.0 degrees Celsius.
Okay, great. Schwender, you go ahead and grab a seat for me. Thank you so much. Pate?
26.4.
26.4. Love it. Go ahead and grab your seat. And lacquer.
Mine's still rising, but
Is it?
It's at
20.7?
28.9. 29.
29. 29.
0.0.
All right, 29.0. It might go up a teeny bit more, but that's good enough. All right, go ahead and leave those there. All right, so those folks took care of that for us. You should have this data written down. I'll give those folks who are our volunteers a chance to write that down while I turn off these Bunsen burners. Boom. 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 All right. Okay, so we're going to use this data to learn some information about these metals and a new term. It's going to be a wonderfully fun time. First, we need to calculate some things. We need to first calculate the delta T of the water. Oh, wow. My smartboard is a little saucy today. Wow, that looks like a scary face. This was supposed to be a circle. Okay, all right. Delta T of the water, delta T of the water. What does delta mean again? What does that? That means change. It means change, okay? So remember, delta, okay, this little, the triangle, it's a Greek letter, delta, means change. So I basically want you to tell me how the temperature changed. For the first one, okay, 25.7 to 27.0, what's our change there? What's our change? What's the change between that? see here. Austin, why don't you get that one for me since that was yours? Pate, give me this one, and Lacker, why don't you get me that one, okay? Austin, what was the change in temperature for yours?
1.3.
Love it, 1.3. Now, I don't care whether he did 25.7 minus 27 or 27 minus 25.7. I don't care about the negative symbol. Just give me the gap. Okay, I want to know the change in those two, okay? Pate,
2.4.
Lacker. All righty, perfect. Okay? So, let's see here. Lead made the water's temperature change the least. Brass medium. Aluminum the most. Okay? Aluminum the most. All right. Well, we'll keep that in mind for now. Let's go over here. My next question is calculate the delta T of the metals themselves, okay? Last time I asked you about the delta T of the water. Now I want to know about the delta T of the metals, okay? So let's think about this. Let's think about this. Here's 25.7. Is that the first temperature? Okay. So the first one with lead started at 25.7. The water went up to 27.0. Okay, so this gap right here tells us the change in temperature of the water, but what about the metal? What temperature did the metal start at? Does anyone know?
100 degrees Celsius.
How did you know that?
Because the water boils.
Woo-hoo! That's pretty good, Mr. Pate. The metal started at 100 degrees Celsius. Here's why. The water was boiling. The metal was in that boiling water for 5 minutes. So at that point, it's going to be the exact same temperature as the water. And so all the metals started at 100 degrees Celsius. So if I want to find the change in temperature of the metal, I got to find the gap from 100 to the final shared temperature, which is 27. Okay? So knowing that, Austin, you'll get me this one. Pate, you'll get me this one. Blacker, you'll get me this one. Okay? All right. So what's this gap right here? Austin, what does that turn out to be? And you can use your phone calculator, no problem. He's finding the difference between 100 and 27.0. 73.0. Love it. Thank you, Austin. You're all done with your volunteer work now for the day, so there you go. Woo! Feels good. Mr. Pate, you went from 100, and what was the temperature shared at the end?
26.
Okay, so what's that difference? What's,
73.6.
yep. Lacker, you went from 100 down to what temp? So what was that change? Thank you so much. Okay, there we go. All right. So we know how much the water changed in temperature. We know how much the metals changed in temperature. We have all the information we now need, okay? All right. So first question is, each metal sample was heated in boiling water until it reached a constant temperature of 100 degrees Celsius, okay? Which metal sample contained the most heat energy at that temperature? This is the new idea. We have not talked about this before, but one of those three metals had the most heat energy at that temperature. Which one was it? And maybe you're not sure and you want to give it a guess. Give it a shot. Lacker?
Are you talking just about the metal itself, or are you talking about like the water with the metal?
Yes. Yes to both of those questions. Sort of like, so one of those metals had the most heat energy, okay? And I'm trying to figure out, was it the lead, the brass, or the aluminum? Which one of the most had the most heat energy? Washburn, you want to give it a shot?
Aluminum.
Why did you say that?
Because when it started, it was way lower, and it was way higher than all the rest.
What was way higher?
The water temperature and the metal temperature.
Oh, interesting. Okay. Well, here's what I like about what you just said. If we look back at these three, lead made the water go up 1.3 degrees. Brass was medium. Aluminum made the water go up a whole 6 degrees. Okay? So aluminum does, in fact, have the most contained heat energy. And how do we know? Because it changed the temperature of the water the most. Okay? Its water's temperature went up the most. It went up more than twice as much as the other two, in fact. Change the temp, I should probably insert, of the H2O the most? So change the temperature of the H2O the most. Using that same reasoning, which of these samples, oh goodness, which of these samples contain the least amount of heat energy?
Lead.
Yes, ma'am. And why was that, Destiny?
Because it changed the heat energy. It changed the least.
Change what the least?
The water.
The water is what? Yeah, that's true, but what about the water? What did it change about the water?
The temperature.
Yeah, okay. Lead changed the water's temperature the least. Okay, there we go. So that must have released the least amount of heat energy. Change the temperature, again, I would say, of the H2O the least. Okay. Now, one thing I would like to point out, okay, all the metal samples were exactly 30 grams. So even though they look a little bit different, okay, so like here's the aluminum, and here's the lead. They look different, but they were both 30 grams. Hey, real quick, how is that a thing? How they have two totally different sizes, but they have the same mass? What the heck? How's that possible? Different densities, right? Okay, so the mass per volume of these two guys is very different. All right, good. Okay. So the mass of the metal is exactly the same. Mr. Pay, how many milliliters of water did you get?
60.
Lacker, how many milliliters of water did you get?
60.
Sweater, how many milliliters of water did you get? They all got the exact same amount of water. Why is that important? Why do they have to all get the exact same amount of water? So you have to keep the amount of water constant, okay? Because you only want one thing to change in between the three. So the only thing we changed was the metal, but we changed the amount of water and the metal. Now we don't know what caused the change in temperature the most. Was it because it was a different metal, or was it because it was a different amount of water? Yep. It's important to keep everything the same so you can compare the changes in temp. You can't compare them. You got apples and oranges unless you have the exact same amount of water. Apples to apples. So here's the real question. That's a tough one. If the masses of the metal samples are equal, how can the different amounts of heat energy be explained? So in other words, aluminum threw the most amount of heat energy into the water. Lead threw the least amount of heat energy into the water. It wasn't that much. How can you explain that? How are those things different, Lacker? Ooh, I had someone say the exact same thing last period. That is on the right track. That's not quite the full explanation, but that is on the right track. Here's the reason why. So conductors, they're more about speed of transfer of heat. Conductors transfer heat. They transfer heat what? Fast, slow? Fast, okay. So let's say aluminum is the best conductor, okay. It definitely sends heat out the most quickly, but at the same time, all three of those metals became the same temperature of the water, so they all sent their heat out. So they all had enough time to send their heat out, so it doesn't matter if one's a conductor or an insulator. All the heat got sent out that they could, okay? So we're on the right track though, okay? Why is it that lead threw out the least amount of heat energy and aluminum threw out the most? Yeah, you want to give it a shot?
Lead's an insulator and aluminum's a conductor.
Okay, so sort of the same side, or the other side of that same coin. So I like the thinking, that's not quite it. And this is a brand new idea, so that you guys have never encountered this before. Lacker, give it another shot. Okay. Well, that's true, but at the same time, they're all exothermic because they're all sending energy into the water. Okay? So they're all sending energy into the water. We're close. We're sort of like, if this is like a bullseye right here in the center, where we're hitting around the bullseye. We're getting there. We're close. No, this is a brand new idea. Brand new idea. Destiny, you want to try it?
I don't have a clue.
She's like, I don't have any idea. I don't know. It's a brand new thing. Okay. Well, this is what we're going to talk about the rest of the class period today. This is called, or this idea is that some metals need more energy to heat up. Okay. Some metals need more energy to heat up. Let me ask you something real quick. So the metal, when I first put it into that boiling water, What was the high? What was the low temp when I first put it into the boiling water?
The water is the high.
The water was the high, okay? So at first, what's happening? Is energy going into the water or energy going into the metal when I put it into the metal into the boiling water? Into the metal, right? So energy is going to be sent into the metal until what happens? When does energy stop being sent into the metal by the water? When they get to the same temp, right? So it goes high to low until they're both high, so to speak. So there's no need for energy to transfer at that point. Just going to stay the same. It's called equilibrium. You guys may have had that from biology a little bit. Okay? So what I'm saying is lead probably got to 100 degrees Celsius in that water after like 30 seconds. Aluminum may have taken 3 or 4 minutes to get to 100 degrees Celsius. It took a lot more energy going into that aluminum for it to get to 100 degrees Celsius. That's why I boiled them all for 5 minutes. It was really because I knew that the aluminum needed more time. And not that it was about time, but it was more about it needed more energy to get up there. So, metals that need more energy to heat up, that means they have more energy in them, which means they have more energy to send out when they're put back into the low temperature water. Low temperature water. And here's the big idea. This next sentence you absolutely want to write down. It's called specific heat capacity. This is the big idea from today's lecture. Specific heat capacity. Specific heat capacity. Specific heat capacity. And I am certain that most, if not all of you, are fairly confused right at this moment. Where you're like, I sort of get it a little bit, but not really. Okay. We're going to talk about this the rest of the period, explain it, and we're going to start getting some math up in here. Okay? So we're going to start getting mathed up today. Start getting mathed up. All right. Let's officially start Thermochem notes number 3, the heat equation. Okay. So this is where we're transitioning over to our notes. So this packet, you'll probably do a practice problem or so in it later this period. But I would put your packet to the side, and we're going to officially use the notes right now. Okay, so wherever you take your notes in, blank paper, what have you. So specific heat capacity. That is the amount of energy needed to change the temperature of 1 gram of a substance by 1 degree Celsius. Specific heat capacity is the amount of energy needed to change the temperature of 1 gram of substance by 1 degree Celsius. So that's the official textbook definition. Again, does that help you understand exactly what we're talking about? Probably not quite yet, but this is what it is officially defined as, specific heat capacity. Sometimes I'll say, or how cheap or expensive it is to heat or cool a substance. So the specific heat capacity will tell you how cheap or expensive it is to heat or cool a substance. The units are joules per gram degrees Celsius, or if I wrote that out further, joules per gram degrees Celsius. And I'd like you to think of this as sort of the currency of heat. Sort of the currency of heat. You don't have to write this in blue, but here's what I mean by the units. Joules over grams times degrees Celsius. Those are the units. All right. So, let me explain what I mean by cost. You guys big fruit fans? You guys like fruit from the store? What's your favorite fruit, Destiny? Bananas, okay. Second favorite? Apples, great. Okay. If you go to the store and you buy bananas, they're like X number of dollars per pound. Honestly, they're probably like $1 per pound. They're really cheap. Really, really cheap. I'm sure someone's mom's going to hear this lecture at some point and they're like, oh, he does not know the prices of groceries. They're very cheap, okay? Bananas are very cheap. Apples are a lot more expensive per pound than bananas, okay? They just simply have different costs. So it's like, I'm making these numbers up. Let's say it's $1 per pound of bananas, and it's like $3 per pound of apples, okay? That's just simply the cost. It's just what it is, okay? It's a ratio of dollars to pounds. It's just a ratio. In the same way, heat capacity is just like a cost, okay, for how much energy you need to change the temperature of something, okay? So some things are cheap, some things are expensive. It's the way that it is. Bananas, apples, whatever. All right. So I want you guys to think of heat capacity as like a price or a cost. Now, don't write anything down here yet. I'll tell you there's one thing you need to write down. Let's just talk for a second. If you think about mac and cheese, like if you ever just thought to yourself like, oh man, I could go for some mac and cheese right now. Okay? Are you going to be able to make mac and cheese in the next 30 seconds?
No.
What? Why not?
Because it takes longer.
It takes forever to heat up that water. If you put a pot of water on the stove, you turn on the stove, if you come back 30 seconds later hoping the water's boiling, you've clearly never used a stove before, okay? It takes forever for that water to boil. You ever wondered why that is? Why it takes forever for water to boil? It's because, it requires a lot of energy, because water has a really, really high specific heat capacity. It's got a high price. It's bougie, okay? It's pricey. Water's heat capacity, write this down, is 4.18 joules per grams degrees Celsius. 4.18, 4.18, 4.18. I'm going to say this number like 12 times right now to burn it into your brain. Washburn, you better 4 your 0.18 or you better get out of here, okay? Hey, man, if you ever 4 my 0.18 ever again, I will 4 you in the 0.18 before you can count to 4.18, okay? Hey, all right, guys, I know we're all 4. I know your point. I know you're 1.8. But we got to calm down. We got 4.18 ourselves out of here, okay? 4.18, 4.18, 4.18, 4.18, Calvin Klein. Okay, 4.18, 4.18, all right? Don't forget that number. It's sort of like the density of water is, there you go, 1.00. You needed that for quizzes. You had to have that stored upstairs. 4.18 better be burned up here, okay? Get it upstairs. For the record, here are all the things that do not have a heat capacity as high as water. Ice, iron, gold, brick, copper, rocks, glass. Water is a super high heat capacity. It's roughly 5 times the heat capacity of a rock. Okay? Rock's all the way down here. It's not even close. Water's got a really high heat capacity. It just needs a lot of energy to heat up or cool down. Okay? So that's the way that it is. All right. Here we go. Q equals MC delta T. This is the center of your chemistry life for the next 3 weeks. Q equals MC delta T. You guys ready for a dad joke? Oh, baby. All right, check it out. You guys check this out. Q equals MC delta T. Also known as Q equals MCAT. There you go. See it? Because it's a little kitty nose with little whiskers. You guys get it? Oh my gosh, Mr. Pilcher. Oh my gosh, I can see Miss Enders. She is peeing her pants laughing so hard right now. Calm down. I know it's really funny, but we have chemistry to do. Look at that. Okay? Q equals MC delta T, or if you're real classy, you'll say Q equals MCAT. There you go. There's a really nerdy way to remember that. So you're sitting there thinking like, wow, that's a really bad joke, but at the same time, it's going to be a little harder to forget. It's Q equals MC delta T if you remember Q equals MCAT. Let's break these down. Okay? Q equals the quantity of the energy, of the heat energy. Please notice, it's always got to be above 0. If you get a negative Q, something has gone wrong. You should never get a negative Q. So I just put a little greater than 0. It will be in joules. Your Q is going to be in joules, that capital J. M, a familiar friend, stands for mass. It's going to be in grams. It's going to be in grams. C is that new one. That is specific heat capacity. That's got the goofy units, the joules per grams degrees Celsius. And I believe you guys all know what delta T is. What is delta T? Delta T. Delta means what? Change in temperature. Again, this one should also be positive all the time. So I don't care if you subtract the final temp versus the initial, the bigger temp minus smaller. Just make sure this is always a positive number, okay? I don't care about the negative sign. Just tell me how much the temperature has changed overall. So delta T and Q should always be positive numbers. And so what's going to happen is, I will give you 3 of these variables for various problems. You will have to find the 4th. So we're going to get all mathed up. We're going to get all mathed up here. You guys got all this here? Nope, not even close. We're going to do some practice math problems. It's going to be a good time. Oh, baby. We're excited. Mr. Pelcher, it's so good to see you on a Monday. I haven't seen you in a week and a half. I was just really hoping we were going to do some math today, and you guys are going to get your wish. It's going to be a good time. Right? I can tell. I can just feel the vibes in here, the energy, the excitement. All right. We're ready. Here we go. Now, before we even do any calculations, you see this number? You guys think you'll ever have that many sig figs? No. If your calculator tells you this, I know you don't know all those sig figs. Deep breath. You're about to get some great news. You really are. We're kind of done with sig figs. Like, done with it, except for the semester exam. We're pretty much done with them, okay? From now on, let's just get a couple of sig figs after the decimal. How does that feel? Does that feel good? We'll just call this guy 42.44. But I had 4 sig figs times 3. Nah, just don't worry about it. Let's just get a couple of sig figs after the decimal, okay? You don't have to write any of this down. You don't have to write any of this down. But just to clarify what I mean, so like this, gravy, gravy. See this guy right here, be like, wait, Mr. Pilcher, but you said only 2 decimal places. No. 2 sig figs after a decimal. So if you had this number here, write out, remember those are leading zeros, they don't count. So give me that 3, 6 right there. I want to see the first 2 non-zero numbers after a decimal. Does that kind of make sense? And if you ever got something that's like 3.0, give me one of these, put that 0 there so I can have a couple of sig figs after a decimal. Are we all clear? So I'm saying that we're done with sig figs, but at the same time, if you give me a hot mess like this, where I know you don't know all those sig figs, that might get you dinged a little bit on a quiz score. Does that make sense? Don't give me a hot mess like this. Give me something pretty like this. Okay? This is what I want. Something like that. All right, now that I mentioned that, let's go ahead and do some calculations. Oh, goodness. Come here. My smart board is a little saucy today. Got some Monday sauce. All right, here we go. How much heat energy, okay, the moment I see this, I'm thinking to myself, hey, this is what I'm looking for, heat energy. That's my Q. It's looking for Q. It's needed to raise the temperature of a 425 gram aluminum baking sheet from room temperature, 25 degrees Celsius, to 200 degrees Celsius. Aluminum specific heat is 0.897 joules per gram degree Celsius. All right. Okay. Stickney, what am I solving for again? Love it. So I don't even have to rearrange this equation. How nice of Mr. Pilcher for the first practice problem. Stickney, what's my mass? Look at you, smarty pants. What's my C? Love it. Specific heat capacity. What's my delta T? Why is he picking on me so much? Delta T.
Is it?
Like both of them at the same time? What do you mean? Yes. It's the difference between those two. So 200 minus 25, that's going to come out to be 175. You plug this hot mess into your calculator. Somebody do that for me. I see lots of pause on the phone calculator. Sounds good to me. Somebody help me out.
66,714.
Look at you. I know your calculator gave you a bunch of numbers after that second decimal, but you just went to the 0.38 like a boss. That's what I need. Slap a J on there because these are joules. This is Q after all. And here's me. Here's what I love to do. I love to put that unit on there, put that J, and I put a nice little box. I'm putting a box. I'm putting a box. Be like, boom. Now I'm done. Mic drop. That's what we're looking for, okay? Yes. 66,714.38. Let's do one more practice problem together before I let you guys get that 3-question quiz in. How about it? Next up, what is the specific heat of a substance? Now, this right here says just specific heat. I didn't use the whole phrase specific heat capacity, but I'm referring to the same thing, okay? So I'm looking for C. Of a substance that absorbs 2,500 joules of heat when a sample of 1,000 grams of substance increases in temperature from 10 to 70. Let's see here. Mr. Mitchell, what's my Q? Woo, yes sir, he knew that because it said joules, didn't it? 2,500 is my Q. That'll be equal to, what's my mass there, Mr. Mitchell?
1,000
Yes, sir. Do I know what my C is? No, that's what it's asking me for. So I'm just going to go and put times. I'm just going to put a C right there. So I'm keeping a variable in there, but I don't know what it is. And what is my delta T there, Mr. Mitchell?
60.0.
Yep. Yes, sir. And again, he took the 70 minus the 10. That's where the 60 came from. The difference, oh my, the difference between these two. Okay, well, I'm going to simplify this a little bit. I got 2,500 is equal to 60 times 1,000 is 60,000. There we go. Washburn, what do I need to do to both sides to get that C by itself?
60,000.
Yep. Divide both sides by 60,000. 60,000 here. 60,000 here. Now tell me my C is equal to what? Oh, goodness.
0.41.
0.41? I love it. C equals 0.41. And the units on that are joules per gram degrees Celsius. Box, put in the box, boom, boom, boom. Call it a day. Now, a couple of things. For practice tonight, you're going to be working on, where's that worksheet? There it is. Your title at the top is different. It's called Heat Equation Problems, worksheet number 1 is the next page. This guy right here. Okay. I'd like to point something out. Here is a chart of your specific heat capacities right here. Okay. So you might be working with something like, you're like, Mr. Filter, I can't solve this question unless I know the heat capacity of lead. Like, well, it's in the chart. So you might have to go back to this chart as you're doing practice problems. Does that make sense? Okay. Hey, heat capacity of water is what? 4.18. There you go. All right. So I will go ahead and take your 3-question lecture quiz right now. It's a pretty easy one today. Please use your notes while you're doing it. Remember, you can't use your notes for weekly quizzes, but 3-question quizzes, feel free to bust those notes out. Once you take care of that, virtual folks, get on out of here. Practice this worksheet. You live folks, do your 3 questions. Practice this worksheet. And then we're good to go. So I'll see you guys tomorrow.